But what does everybody have now? Frickin' phone that does what? Yeah, okay. Thank you. Or, not everybody has a phone, but everybody has a phone. So. Oh, let me pull this up. Oh, I'm logged in. Holy shit. That's crazy sauce. Yeah, there we go. Yeah, do it. All right. So 13.4. 13.4 is basically kinematic applications of vector functions. And let me say this again. Has anyone ever done any physics? Kinematic formulas? Do any of you guys know what that reference is? That's just equations of motion, yes? So for example, you start with acceleration due to gravity on Earth is a constant. Then if you integrate that, you get the formula for velocity due to a falling stone or something. Then you get general kinematics in a gravitational field. I'm not going to start, let's back up. I am basically teaching you physics, but the mathematical part that physics needs is what. So 13.4 is, all this shit we learned, here's some physics applications, right? So it doesn't really give you anything new, it just repackages it for physics problems, yes? So I do want to say a couple things. I am perfectly sane. Okay, let's see. I wrote a couple notes down for myself. There they are. Oh, I should probably let you guys in on this. Yeah, I think this is where they actually do vector integrals a little more. When we talk about it talks about Newton's second law, which is the sum of all the forces acting on a mass will cause an acceleration of the mass. So there's a formula in physics, F equals ma. Yes? FEMA. So if you do any physics, this thing is going to rule, like the first half of the first course you take. It's going to be ruled by this guy. Ruled by this guy and these guys. Yes? Anybody? Sorry. Oh, sorry. Okay, I'll stop. So a couple of important things that section 13.4 defines. I'm not going to run through. It does talk about harmonic motion, if I remember correctly, or at least periodic motion. Right, so a periodic motion, so very often harmonic motion or circular motion is definitely periodic motion. There's a certain period to it. Every second I'm back here. There I am, one Mississippi, back here. I think one of the most important things it discusses, and I really don't want to run through the whole gamut, it takes the acceleration vector and it breaks it down into a tangential acceleration and if I remember correctly, almost Jeff. This is sort of based on this, but then you rewrite it to be this. Okay. And this would be the normal component of the acceleration.
Is that K? Is that what the...
Yeah, what is that? Yeah, that's from the curvature, exactly. I'm trying to write it better. Oh, screw it. I'm not going to write it better.
Is it V squared or U squared?
Do it again, sorry.
The kappa, is it?
V squared, yeah. This is the velocity. Okay. And velocity was the derivative of r. Yes?
Yeah.
Okay. All right. I don't want to say much more than that, but I just wanted to very quickly, it is extra credit. You do need to read it. It's a bunch of formulas using a lot of the mathematical processes we talked about already, but they just use it in physical situations. So it's going to be a little bit word problem-y, that section, if you want to give it a try. But it's still going to be basically plugging and chugging into formulas. I'm just not going to spend lecture time. I obviously am not. I just gave that to you, and I didn't derive it for you. So you could derive this formula. Okay, let me stop for a minute. You guys with me? So again, this is 13.4. 13.4 is extra credit. If you want to try that out, feel free. When does that homework due? Day of the fun. If anybody on WebAssign wants to try it out, and I haven't put it up, just remind me. Send me a normal email saying, hey dude, put that stuff up. And I'm like, okay, sounds good. All right. Help me help you. Help me help you. Thank you. So, today I want to talk about something exceptionally nifty. My absolute favorite part of this class is what we're about to get into. So I don't know how that makes you feel. There we go. In Math 180, let me ask you this. Let me see what you guys tell me. What is a picture that you draw like the most in Math 180? There's a certain picture that you draw like all the damn time when you're doing 180. If you learn integrals, so if I'm talking about 180, I'm talking about integral. What picture? I'm going to do this picture. Yes. Look at this picture. You guys agree with me? Good God! If I just drew this picture and I said, what would I use to discuss? I would use it to discuss area. I would use it to discuss integration. Yes? You guys with me? So do you all agree? In 2D, I've only got a line to walk on. Yes, here's my axis I'm walking on. And the top of my head is like the output. So if I do this, I get a sine function or something, yes? And I show off how fantastic my knees are after a lifetime of playing basketball and tennis. Can't really get down there too much. You guys kind of with me? All right, maybe. And I only live on that line. Yes?
Surfaces.
Oh, God. Oh, boy, he's selling it big. All right. Thanks, man. So now, for us, we're going to have not just a function of x, because this would be, an input would be a number from the x-axis, and an output would be a location on the y-axis, yes? So if I have an input of x1, f of x1 would be that output. Is that cool? Of course it's cool. Because that's even below 180. That's just basic graph. So read with me. So in Calc 3, we're allowing ourselves to live in the real world, which, as far as you can tell, has 3 observable dimensions. Yes? So now my input is the entire floor. Yes? Love you guys so much. So for example, if I define a function of x and y, so this could be f of x equals who knows what, right? If I define a function of x and y as, for example, x squared plus y squared, yeah? And let's say this is the origin. This is 0, 0. You guys all see the floor? You don't see the floor? Sorry. Somebody was on. The floor. We're good with the floor, yes? So I'm at the origin. You guys with me? So this is the x-axis, and that's the y-axis. Is that cool? So I got people on my x-axis, I got nobody on my y-axis. Is that cool? Yeah. Okay. So 0, 0, what would the output be? I'm at 0, 0, correct? The output would be 0. If I move over there to 1, 2, 3, 2, where my man is, 3, 2. Sorry, man. He's like 3, 2. What would the output be? If my input is the point 3, 2, what's my output? 13. 13. Get gas. You guys with me? Can you guys imagine that? So as I move away from the origin, my output's only going to do what? Get bigger. Where is the output of this the smallest? Origin. The minute I move, even if I move in a negative direction, of course, yes? Because it's all squared. Okay. So what's the shape of this going to be? No, it's not going to be a circle. Come on, you can do better than that. If I said, what would a trace of this be at some height, circle is the correct answer. That's not what it says.
So it's like a dome. It's like
A bowl, upside down dome. I love it. Somebody had a dome and they turned it around. It's a walk. It's a whatever the shit. Yes, it's a dome that's turned upside down. Can you guys see that? At the origin, what is f of 0, 0?
But then why does the Z?
Say again.
Why does the Z choose?
Oh, what do you guys think this is? Real quick.
It is
Y equals 2x plus 7. What did we replace y with?
F of X.
Yes. So think backwards. What is this really?
Z.
Z. Kick ass. So that's why when I'm at the origin, what's my height from the xy plane? 0. The minute I move around, it's going to go up because I'm squaring my inputs. Does that make sense? The minute I'm not on the origin anymore, right, it's going to be high. So, is everybody with me? It's exactly like on the x-axis. I mean, real quick.
Like a Bravo.
Get out of my head. When will this be the lowest? At the input of 1, correct? The minute I move away from that, it's going to go. The minute I move away from x equals 1, either direction, and it can only go left and right, correct? For my inputs. I've only got one dimension of input motion. Does that make sense what I just said?
Yes.
Love it. The minute I move away from 1, my output is going to do what?
Go up.
Of course. You know that for 2 reasons. Number 1 is a stupid upward parabola, so of course it's going to go up. We know that's what they do. Secondly, you know the minute I'm away from 1, I'm squaring the difference from 1. That's going to be positive. It's not going to be 0 anymore. So I can't help but go up. And the further I get from 1, the bigger the square of the distance is. Yes? You guys with me? So, coming back to this one, if I'm at the origin, the output is 0. What if I'm at the point 1, 0? 1. What if I'm at the point 0, 1? 1. What if I'm at the point negative 1, 0? 1. What if I'm at 1? Okay. So, real quick. Origin. Things right here. Roughly. Right here. Origin. Right? Move over 1 in any direction, including diagonally, which we could do. Right? If I move over 1, isn't the height going to be bigger? And if I so 1, 1, negative 1, negative 1, it's going to be at 1 at each of those points. Is everybody with me? Love you guys. Love you guys so much that it hurts sometimes. So real quick, can somebody give me this guy? Too bad. We're past that shit. Let me bring this guy back. Bring this guy back. Let's figure out what we already figured out. Is that cool? I'll just kind of copy down what we did already. Is that cool? Can somebody give me another 2 inputs that has a 1 output? Let's try it. Let's do it again. So give me 2. Give me 2.
Oh, both the square root of 1.
Both. I'm sorry. That's what you said. Both. Like this. Yes.
Yeah.
And what do you get when you do that? If you do it the square root of 1/2, like Ellie said, and she's like, if you would have just listened to me, Jeff, it would have been so much easier. Because what do you get? And this is a square root of 1/2. Is that cool? But I just wrote it more like, trigonometry. But it is the square root of 1/2. What's the square root of 1/2 squared?
2.
Plus another half, because you square the square root, you get 1. Yes, of course. So, you guys with me? I need you to be with me. Okay, let me come back. Do you all agree? How do you guys feel about my inputs for my function now being a plane? If my function is based on one variable, my input is that variable's axis, correct? So if I have an f of x, I can only go on an axis. I can only make my inputs 1, 2, 3, 2, 1, 0, negative 1. You guys with me? Okay, I'm so happy I didn't trip over. If my function allows for 2 inputs, geometrically, that's a plane of inputs. So if I say I want x to be 2, y to be -1, I am actually at the point 2, -1. And then when I say what the output is, I can think of it purely mathematically. Couldn't you put a 2 and a -1? I'm sorry, I keep pointing at a monitor. Couldn't you put a 2 and a -1 and get a number? What's it mean geometrically? At the point 2, -1 in the plane, I go up whatever I get. Yes? 5. You guys with me? You guys really with me? So I love some of you guys are like, no, but maybe you'll say something that makes sense. So I'm at the origin, I'm at 0, 0. If I move away at all, I go up. If I go 1 away from the origin, I'm at a height of 1. You guys agree? Did we just figure that out?
Yes.
Would you all agree then that at a height of 1, if I slice whatever the picture looks like, I should get a circle? In fact, at every height, I should get a circle. In fact, let's check that out. Which part of this function are we saying identifies height? F of x, y, or z. I love it. So if I wanted to be at a height of 1, I would just investigate this. Is this in the xy plane, knowing that this is my function? Is this in the xy plane? No. It's 1 above the xy plane, yes? If this is my function, and I put a 1 here, what am I saying my height is? 1. So is it on the xy plane? No. It is a slice at a height of 1. Yes?
Isn't previously this formula would mean that it has a radius of 1?
Of course. And that's exactly what I just said, correct? If I start at the origin, and you go out 1 in any direction, we sort of saw, well, it makes sense, the output's going to be 1.
Oh, now we
Yeah.
just...
Yes?
So when you say plane, you're specifically talking about the z height, like.
Yeah, so you can think of it as the intersection between this function and z equals 1. And how do I know that's what this is? Because what did I replace z with? Freaking 1. So of course it's the intersection of z equals 1 and this function. How we doing? Let me do this. Yes.
It's a flat slice on a three-dimensional space.
Let me actually give you the picture.
Okay,
Let me get it set up. Hold on, everybody. Talk amongst
You're
yourselves.
almost there.
I'm with you. This is trippy. This is very trippy. How you feeling over there? You started off. Okay, everybody. Okay. Good. You don't see it yet. I got to change my function. Conjunction, junction. Okay. I don't want to forget you. I don't want to forget you, man. Stay there. All right. What was this? X squared plus y squared. Chimney chumba. There we go. How did I even do that? That basically summarizes me playing a video game. How did I even do that? Okay, that's perfect. Perfect. Okay, let me just put that there. Turn this on. Turn that off. And here, I guess I'll let you in on this, is what this looks like. Now here's what's really cool. So, this would be a very strange topographical thing. There are not a lot of geological places that look like this, correct? If I turn this guy around, that would make a little more sense. There might be something that's pretty approximating a bowl like this in geology. Yes? Where are my geologists at? Mark, I mean, don't do it. So if I turn this other piece on, you're not going to see anything yet. Because what I've done, do you see here? I've set the height to be k. And right now, the height is 0. And watch what happens. Boop, 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 boop. See? So as I move up, so if I stop at 1, I get the one we were talking about. At a height of 1, that is the slice through the picture, yes? That is a level curve. That is where they have the same, you can do it, Jeff. Height, there it is. If you're talking about temperature, we would call, you could kind of graph out the temperature, and you would say the line that designates the temperature is equal would be the isothermal. I think pressure is isobaric. If you look at a terrain, you guys have all seen a terrain map, yes? What do you call it, topographical map? If you just go to Google Maps, yes? Or Apple Maps? I don't know what this shit Apple Maps look like. I can only assume it's terrible. So turn on the terrain. This isn't the best, but if I zoom in a little bit, I thought it gave me, maybe I'm wrong. Maybe I need something bigger. I thought it gave me lines. It sort of does. Yes, it does. But does it actually, see these lines? So if I were hiking and I walked along this line, I am staying at a constant height. You all agree that if I try to create a mathematical function that represents, I'm pretty sure we're in around Coles here, or in Mission Trails, is that where I went? That would make sense. If I try to make a mathematical function, it would be really, really difficult to do so. You guys agree? So that's why these level curves are much more interesting than my little bowl that's got these circular ones. You guys with me? Mm-hmm. So I can always designate the areas on my 3D image that have the same height with these lines. And we call those level curves because they're curves that represent where they are at the same level. Okay. This is a 2D map representing a 3D idea. Okay, lock it. You guys, how are we doing so far? Are we okay? No? Screw you, Jeff. You suck. Let me try something besides Google Maps. I'll try Google. Let me Google. Not Google Maps. There we go. Topological map. I love how you can almost spell something. Okay. There we go. Is that basically what we're just looking at? But it's got numbers, so it's a little better. You can do it. There it is. So now I can tell if I'm anywhere on this, if I just stay on this line, I stay at 650 feet up. Yes? Okay, so the functions we're going to be looking at are not going to have anything quite that weird. They're going to have to be a little bit well behaved. Yeah, is that okay? Let me see, let me put the other function I had in here. Let me turn this guy off for a second. Okay, now watch this. You ready? So now that is just the level curves. That is the slice at that height. So do you see how I'm a height off the XY plane? Yes? So if I move up and down, you can kind of see how this thing gets mapped out. Now this gets really trippy. So can you imagine it's sort of like two cones that are kind of shaped a little weird that kind of stick out of this graph? What do you think happens? Are you guys kind of with me still? What do you think happens right here? Pop! What the ever-loving shit? So now, can you imagine? You have a flat thing, and then this thing sort of comes out of the flat plane, yes? If I go down far enough, everything's going to be at the same level, correct? So this means there's a little piece in the middle that's doing something, but everything around it's kind of like doesn't have a jutting position. This is the curve here, so it's sort of like flattened out in the middle a little bit more. So let's see what it actually looks like. This function, by the way, very trippy. Turn this on. Do you see in the middle how there's a valley? You guys with me? Mm-hmm. So if I go back up, it's kind of doing these two cones that are sticking up. Yes, the cones of Dunshire, or whatever that is. And then if I go down, let me get that reference. If I go down, then these kind of blend together here. See that? So now it's focusing on that dimple in the middle. That has the same height inside. Now what gets really trippy is, I think this one. Let me turn this off. Oh my gosh. No, it's not this one. It's another one. Darn it. Yeah, another one does it. Trippy. Yeah, I got to bring him in later. But this is kind of nifty. This is like the, I don't know what this would even be. This is like an invisible thing and we're scanning it. Do you see what I mean?
Sonar.
Yes? Sonar? Yes, I like it. Something like that. And you turn them on like, oh, that's what it looks like. Okay, let me stop for a minute. So, In 2D, we have inputs and we have a line that can kind of like hover over those inputs. Yes, they represent the outputs. Are you with me? In 2D, we have a line of inputs, the x-axis. And then over that we have some kind of curve. It can go under, of course, also, but we have this curve of outputs that we can call the height. Yes? Now we extend that to 2D in the same damn thing. Now whatever direction I go in, I can have this curve above me that represents, and I always think of it like a tent or something, you know, some kind of a covering you have over. Yes? Okay. Like it.
So you're saying if we integrate over f of x of y, we can get the volume of this.
How many directions do you have to go in?
I mean, you just scan it in one.
So you're getting a little ahead, but in 2D, I just had to integrate as x changes, and I can capture all that.
Yeah.
In 3D, don't I have to go both x and y? Then I need a double integral. What the fudge? Okay, I love you guys so much. Something else to point out. So today I'm kind of treating as an overview what we're about to get into a little bit, and then we'll get into some more specific stuff here in a minute. Do you guys notice? Let me look at this. Oh, by the way, let me do this once before I forget. If I just look at the XY plane, this gets really trippy. So this is us hovering over it. It's gone invisible and we're scanning the outside of it, yes? So this is always kind of trippy when you do this. Woo. It looks like, what do you call it? The, not a CAT scan, but like a MRI or something like a, is that a CAT scan? I can't remember. Showing off my medical ignorance. Okay. I'm American, we don't know because we don't have enough insurance to know. Okay. Little commentary. Okay. What else was I about to show you? I just forgot. Darn it. Oh, yeah. Do you see how, let me see if I can see a good place for this. Yeah, man. Do you see how right here, let me look straight on. That looks pretty good, yeah? That looks pretty manageable. Do you guys agree? That looks manageable right there. That looks sort of like repeated parabola going on, yes? Sort of, or maybe even almost sinusoidal, but not really, because of course it doesn't really go back up. But that's certainly more manageable. Do you guys see how, if I want to talk about the derivative, it depends on which direction I go? Like in 2D, when we talk about derivative, we're meaning as you move along the x-axis. Why do we say that? Because that's the only thing you can do, yes? In 3D, I could talk about as I move along the x-axis, what's my function doing? Or I could talk about as I move along the diagonal, what's my function doing over me? Or I could talk about as I move along the y, or this way, or at some angle. You guys kind of with me a little bit? Have you ever gone hiking? Question mark.
Yeah.
And you're at a place where you're hiking, where you're looking straight forward and you can go up. And you look this way and you can go down. Yes? That has happened if you've ever gone hiking a little bit. Even if you're just walking around some of the frickin' neighborhoods. Think about Mission Hills or something. You're walking and you look this way, it's like straight up. You look that way, straight down. You look over there, straight up again. So, when you have these surfaces, when we get to the point where we're talking about the derivative, I can't just say the derivative. I have to give you a direction. Because if I'm in the situation where I'm on that place where I'm hiking, and I can either go straight up here, or I can go straight down there, or I can go straight across that way. If I say, what's the derivative? You're like, what the hell? What do you mean? You have to tell me which way to step. If I step this way a little bit, it's positive. If I step this way a little bit, it's zero. If I step that way a little bit, it's negative. You guys with me? So later we're going to have things called directional derivatives. Who knew? Yes?
So derivatives are dx, and it's x because it's in 2D.
So what we're going to build is the idea of a partial derivative. Oh, shit. Do you all agree with me that if I'm standing at a location, and if I go straight, I would go up? You guys see that in your head? If you go straight, you go up. And if you this way, you go down. You with me? You with me?
No.
No? Yes? No. Okay, how can I demonstrate this? Let me get another function in here real quick. Bum, 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 bum. Bum, 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 bum. Bum, 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 bum. Ooh, there it is. Let me see. Yeah. Okay. Has it got this in it too? Yes, it does. I think this is one I need to give it a little bit of a boost. Yeah. If I'm standing right here at the origin, you with me? If I go at a diagonal, I'm going to go up, yes? If I go at the diagonal this way, I'm staying flat, yes? Or I'm actually going down, to be honest. Do you see that? Okay. Is that okay right there? So if somebody asks me, what's the derivative of this function at 0, 0, that's not a good enough question. That is too broad of a question. You have to tell me what direction. If I said, what is the derivative if I hold, this is not the greatest example for this. If I hold x constant, so I only move along the y-axis, do you see what I mean? Really want this to make sense. I could only move along the y-axis, which means I would make x constant. Does that idea by itself make sense? I could actually make x whatever constant I want to and talk about the derivative in the y direction, yes? So what I just said, the phrase I just said, the derivative in the y direction, does that phrase make sense with everything we've talked about so far? That is a partial derivative. A partial derivative is hold one variable constant, look at what the other variable does. Or look at the, not the other variable, but as I change the other variable, what does my surface do? Yes? If I change the y variable and my surface goes down, the partial derivative with respect to y is negative. Yes?
But would you just substitute the value for x and take a derivative as usual?
No.
No?
No.
I thought it was easy.
It's okay. We'll get there. Alright. Because if you do that too early, then too many things become 0.
Yeah.
You almost never want to plug a number in first. Yes. Let me stop for a minute. So this first section is only concerned with surfaces. And what is a surface? It is a function of x and y. I like it. So before today, we were dealing with equations like x squared plus y squared plus z squared equals 9. What was that an equation of? Now, technically, that is a surface, but it's not a function of two variables. Could somebody tell me very easily why a sphere would not be a function of two variables? What does it not pass?
The line test.
Vertical line test, yes. This function passes the vertical line test. Yes? That's why it's a function. Plus, you could solve for z, so it's automatically a function of x and y. It's a function. So we're kind of narrowing our scope of what kind of function, of what kind of relationships we're considering. While at the same time, we're going to expand what we do with them. Yes? Okay, I love it. I love it. I'm the only one in the room. That's okay. All right. Let's see. What else did I want to say? Blah blah blah. Oh, okay. Let's come back to this. All right. Let's bring it back down. Let's bring it back down. I basically just talked a little bit about various things we're going to do throughout chapter 14. So let me bring it back down. Let me bring it back down. Let's see. What did I want to say here? Oh, I already said that. Good, good, good. Oh, let's do this. So what if I had this thing? Now that we've established, much like I could have f of x equals x squared or something, what's the next thing you did was to graph that, yes? And what's the next thing you did kind of like at the same time? Talk about the domain. You with me? Now, obviously, functions of x and y are going to have funkier freaking domains, yes? Because their domains are regions in the xy plane. Let me say this again. Whenever I'm dealing with a function of x and y, the domain is going to be a region in the xy plane, because where do the inputs come from? The frickin' xy plane. So what is the domain of a two-dimensional function, f of x? It's a region of the x-axis. Could be the whole x-axis, it could be 0 and to infinity, whatever, yes? You guys with me? I love it. You would, Jeff. Can somebody tell me, very obviously, what part of this gives us trouble? The natural log, yes? X dude is fine. He's like, whatever, man, take whatever you want to make happen, cool. But what's got to be true about the input of a natural log? And what's the input of the natural log here? Let me just do this. Inside must be greater than 0. True? So what I always tell students, if you're trying to figure out the domain of a function, just say in English what must be true, and then write what you just said in Mathish. So the inside must be greater than 0. Can you guys see what that's pointing to? If I do some solving, maybe. Does anyone see anything you can do with that? Because my answer again is going to be what? What's my answer going to be? I love you. But what did I say earlier? And the x-axis is a region of the x-axis domain. So what's my answer going to be? It's going to be a region of the floor of the xy plane, yes? So it could be that only a circle works. Maybe just a little circle in the xy plane works. If you try to go outside of it, you get negative square roots or something. Yeah, we don't want to. I don't think you want me to allow complex inputs. Do you? That would have been fun. But you guys kind of with me? Maybe a little bit. Screw you, Jeff. You suck. Okay. Real quick, side note. What's that guy's domain? And again, whenever we say this, we're assuming we don't want complex inputs or outputs. Negative 1 to 1, yes? It is an x-axis's best approximation of a circle. It's a radius 1, but it can only go this way and that way. You with me? You kind of with me? Isn't that a region of the x-axis? From negative 1 to 1, inclusive. Yes? Is that cool? You guys see that? If you try to put something bigger than 1, it screws up. If you try to put something smaller than negative 1, it screws up. You get a complex number. We apparently don't want to try to graph complex. I don't blame you. You got to break out the colored pencils. Okay. You stop for a minute. You guys with me? You guys okay? You guys doing okay? For real? For this specific problem, we didn't have to do much math. You just had to realize, if I try to subtract more than 1, this is going to freak out. So I can't let x squared be more than 1. Therefore, x can be between negative 1 and 1. Bam! This problem, I need to figure out, is there something I could graph that would designate the region in the xy plane that I'm allowed to use points from? Like here, couldn't you graph the answer? What would it look like? It would look much like what you're doing, Jeff. That's true. Yes? And this is where, whenever I teach this, I use Dragon Ball. I go, right? Somebody on the other side, okay. Dragon Ball is not a prerequisite for this course. I'm sorry. You're fine. This guy. Let me just say, if I solve, don't I get this?
Yes.
What kind of shape is that? You can do it. Y equals x squared is a parabola opening up. X equals y squared is a parabola opening specifically to the right. And here, x is supposed to be less than the parabola. So,
The left of the parabola?
yes. I had to think about it for a second. In my head, I was trying to get my left and right straight. So if I want to graph x equals y squared, if y is 1, x is 1. If y is negative 1, x is 1. So this is x equals y squared. Am I allowed to equal y squared?
No.
Nope, so that's why I left it as a dotted line. X has to be less than that. So right here, there's y squared, yes? You agree? That's a y squared, you agree? Where the x is less than that? There. So what values am I allowed to use? Anything that's not inside the parabola. Does that make sense? If I try to use, what's going to happen? Can somebody tell me a point that is definitely inside this parabola that doesn't have a 0? Give me a point that is definitely inside this parabola. Here, I'll help you. 2, 1 is definitely inside the parabola, yes? Because 1, 1 is on the parabola, so 2, 1 is inside of it. You guys all see that. Is it in a region that I'm allowed to use? So what should happen if I try to use it? Something weird should happen. So let's try it. Plug in the 0.21. So what do I put right here? 1. Good. People see the first number, they put the first number, but x is 2, y is 1, yep? So this would be 1 squared, 1 minus 2 is? Yeah, negative 1. Natural log don't like it. There you go. You guys with me? This is safe. This is weird shit. Nope, that's why I made it dotted. Because am I allowed to equal? Is x allowed to equal y squared? No, so I can't use any number on the parabola either. Is that cool? If I try to use 1, 1, you all agree 1, 1 is on the parabola? What happens when I use 1, 1? And what's the natural log of 0? 1 to 5. The limit of natural log of x as x goes to 0 is. What's the natural log look like? Can you graph it in the air? Graph it in the air. What's the natural log look like? I want somebody to do this. ln. No. If you graph ln, what's it look like? Yes, I got a few people. Yes, it's this. Yes. What the shit is this? What is this part of it right there? Asymptote at 0. So as x goes to 0, natural log of x goes to negative infinity. Yeah. Okay. If you keep the images of functions, graphs in your head, domain and range questions are easy. Yes? Do you have to do it only that way? No. I'm sure there's another. That's the way I do it. Maybe stop. I love you guys. How you doing? Yes?
So is domain always going to be the function?
Domain will be based on what function composes f of x, y. Is that your question? Like, so why was the domain here restricted? Because our function had what in it? Natural log. If I had a different function, so this is f of xy, what if I made g of xy equal to x times y squared minus x? What's this guy's domain? Does he have any issues? All real numbers, be more specific. They can't say all real numbers because then what's our inputs? Every one of our input is a point. No, don't say numbers. All points in the xy plane. Yes? What is an input for a multivariable function? It is a point. For right now, we're talking about 3 dimensions. Yes? You guys kind of with me a little bit? We could talk about 11-dimensional function. You guys agree this is a 3-dimensional function? How many variables do you see? 2. Where's the third one? G, right? You guys kind of with me? So if I have a 3-dimensional function, I have 2 inputs because the output is the 3rd dimension. Is that cool? So if I had an 11-dimensional function, I would have 10 inputs because the 11th would be the output. Could you graph that easy? No. Could you do the math of it? Hell yes. I love you guys. That makes one of us. I'll be alright. Oh. So let's do this. Can you guys tell me, number 1, is this a function of 2 variables? What can I replace z with? F of x1. So it's a function of two variables. I'm considering z to be the output variable, yes? The output, right? Okay. So I want to address this. You all see three letters, don't you? So some of you guys are out there going, what the hell's up with these people? See three flipping. But it's a function of two. One is a function of the other two. So I would say this is a function of two variables. It's a function of x and y. Is that cool? So my input is the xy plane. Can somebody tell me what this would look like if I graphed it? You guys know. You guys know all too well. Solve for 4. Solve that function for 4. No. Solve it for 4. Get 4 by itself. Do it. Oh, wait. Get 4 by itself. 2x minus y plus z equals 4. What is that the equation of? I don't need anything specific, just what shape. No, it's not a line. It's a plane. There it is. It's a plane. Okay. Let me stop for a minute. Everything we've learned before cannot change. It cannot change. We're just adding to it. So we're looking at a plane. If I solve any plane you've ever looked at before today in this class, solve it for z, you can call it a function of x and y. Does that change what it is fundamentally? No, it's still a frickin' plane. You guys with me? So obviously you should know when I graph this, it's not going to be curvy. Yes? Why not? None of the variables are raised to another power than 1. They're all raised to the first power. Let me stop for a minute. And you all know that ax plus by plus zz equals d is a plane. We know this, yes? You all went through that whole thing. You love it so much. Okay. What is ABC? In ax plus by plus zz equals d.
Normal.
The normal vector. Yes. Native scalars, but together they make a normal vector. I love it. Alright. So what's your point, Jeff? I don't know. Well, how do you think I would graph this if I had to graph this by hand? Besides cry and then erase it and hope nobody noticed it was there in the first place. How would you graph, back in the day, when you learned how to graph lines, what was one way to graph a line? You could find where they hit the axes. Yes, you could find, also known as the x and y intercepts, correct? How did you find the x-intercept? You made y0. How did you find the y-intercept you made? Alright, how do you find the y-intercept? No, make everything else 0. So now we have to extend it. When you only have two variables, you can say it, make x 0. No. If I had 26 variables in my equation, how would I find the w-intercept? I would make every other freaking variable 0. Correct? That brings it in. Every axis is not allowed to go anywhere. My one variable I didn't make 0, now it's allowed to be wherever the hell it's got to be. Does that make any sense? So take a minute and find all the intercepts. I'll just stand here. Good job, Jeff. Find all 3 intercepts.
You should make everything else 0.
Yes, so there's 3 variables. So if you want the z-intercept, you're going to make...
Z 0.
No, if you
Why
want
not?
the z-intercept, you make everything else 0. To make x and y 0 to find the z-intercept.
But I imagine the plane, and let's say there is a
No, you're overthinking.
there's a spot.
You're overthinking.
1, 2, 0.
You're overthinking. If I have any function and it hits the z-axis somewhere, what's true about x and y? What's the value of x?
0.
It's got to be 0 because it's not this way or that way. And what's the value of y?
0.
It's got to be 0. So if I make x and y 0, I'm uncovering where the function is when that's true. So I'm finding the z-intercept.
I see.
Exactly the same way we did in 2D. I can make an analogy between everything we do back to 2D. Everything's just going to obviously be a little worse because now we have multiple directions I can go in, not just a line. Yes? You all look very excited about this. And now, anytime I say I like something a lot, you're going to be like, oh, shit. All right. So what did you guys get? Anybody? What was your z-intercept? Yes, sir. Be better than that.
0, 0.
Yes. Intercepts your points. What's your x-intercept? 2, 0, 0. And what's your y-intercept?
0, negative 4, 0, 0.
Kick ass. So this is the easiest way to graph the answer. We know it's a plane, don't we? Now obviously I would hope that we'd have the right paper, but even doing it with my shitty, what do you call it? Scale. That's the word, John. Is it important that I know that when I teach math? Maybe. X-intercept was 2, 0, 0. Y-intercept, oh, you gotta go back this way, buddy. 1, 2, 3, 4. And the z-intercept is 4. There we go, it's right there. So I get this chunk, that's a piece of the plane, correct? But now I can just sort of do this kind of thing, yes? And it goes off. You could even just do this, to be honest. You can just say it extends off in all directions. You can try to do what you can to make that a nice plane. You guys see what I'm saying? So you can start with a piece of the plane, and the easiest piece of the plane is connect the intercepts. Yes? Those 3 lie on the plane, so if you connect them, those vectors between them that I just drew in must also line the plane, correct? And so that's why visually I get a piece of the plane, and then I can try to extend it. So I'm not going to make you do a ton of that, because it gets really gross really quick. Some of you guys are really good artists, and they look really nice, and then I feel really jealous. But I love it. Continue doing that. But to me, if you have to graph a plane, that's the best way. Find the intercepts, connect them, and then try to kind of extend it. You can kind of see the lean of it then better. Yes? Maybe? No? Screw you, Jeff? Okay. All right. Okay. All right. Now, real quick, what's the domain of this?
All points in the XY plane.
There it is. All points in the XY plane. Because what is a singular input? A point. Yes. So what points can I use? Any point in the XY plane I can use.
Could you say R squared?
Yes. Because that is, the XY plane is also known as R squared. Yes.
How do you write that?
So if I said what's the domain, you could say any point, or you could say all points in the XY plane. You could say XY element of R squared. Yes? Is that cool?
I don't know what element means. But
Oh, I'm sorry.
I could
Element just means a part of, like, if I said give me an element of the XY plane, you would say 1, 3 is an element of the XY plane. It's a member of the set of things that live in the XY plane. Is that okay?
Yeah.
And that little e, that little weird curvy e dude means an element of. Sorry, it's some set notation. Whatever, math boy. Alright. Let's see. Okay. Okay. How we doing out there? You guys alright? You guys alright?
We're taking a break.
We could. Yeah, you want a break? We could take a break. Alright, let's take, what do you want? I'm not doing crazy amount more, so let's say like, well, you want a 10-minute break, 5-minute break? Up to you guys. That would be really silly. I'm not going to do a ton more, so let's take a 5-minute break. And they're going to let us out a little early when you get back, so. If anybody didn't on the test that, I'm really surprised nobody asked. Because it's a problem basically everybody missed. I think there were like 3 people that got it right. Real quick, help me out, guys. How can I make you all see this? Yeah, okay, I got it. Okay. Here we go with the freaking pen again, Joe. Vector, yes? Vector. And you can do this at your desk too. Just take your writing utensil, put it up on your desk or whatever. Do you agree that the vector makes an angle with the book? I'm going to say the book is the XY plane. You with me? Where is the angle at?
Isn't it in right there? Yeah, it's not wherever the shit. It is specifically the closest angle. It's the angle between this and the plane, yes? So if my vector is not hovering over the 1, 0, 1 axis, right? It's not hovering over that. I can't use that. So what do I do then? Well, if this vector was 1, 3, 7, and this is the xy plane, what's true about z in the xy plane?
Doesn't make sense. It's not.
What's true in general? What's true about z in the xy plane? What's the value of z in the xy plane? 0. Yes? Z equals 0 is a functional definition of the xy plane. Just like what's y equals 0 the definition of? Y equals 0. I mean in 2D, sorry. Y equals 0 is a definition for what? X-axis. I think that's what you said. Thank you. You're good. No, I heard at the same time somebody else said a plane, and I realized they didn't say 2D. So everybody with me? If this is 1, 3, 7, it makes an angle with the plane, but specifically, what angle am I talking about? The angle it makes with its own shadow. Yes? The angle it makes with its own shadow. Yes? If this is 1, 3, 7, what'd you just tell me is true about z in the xy plane?
0.
So therefore, the other vector I would use 1, 3, 7, and I would use 1, 3, 0. The angle between those two.
Well, so one question is,
If you use 1, 0, 1, that's off to the side. That's not going to get the right angle. Yes? Oh, I'm sorry, yeah. Which one was it? 1D? Yeah, 1D.
That was everybody's 1D on the test.
so like the vector, like the y would
Just take your vector and put
Make x 0, and that's the other vector you want to use.
Oh,
The shadow. I think 3 people got one. Huh? Well, you're one of the 3. Good job.
No negative marks there.
Oh, there you go. Okay.
I can make
Does that make sense for whoever asked that question specifically? I don't remember who asked that question. Okay, we'll never know. So hopefully that makes sense. Oh, did I turn this guy back on? Yes. All right, guys. And then what do you think about this function here? Can you find that guy's domain?
well, x and y here, they don't depend on each other, right?
No, yeah, exactly. Every single function we've looked at in 2 variables, x and y are not dependent on each other at all.
So can we
Because
just,
there's no reason they should be. Good.
so can we just
You're overthinking. One way to look at this is, could x be 5? You guys see that x could not be 5, correct? Because then you're subtracting 25, and minus y squared is going to just subtract more, so you're going to get even more negative, and we don't want to bring complex numbers in. Or at least that's what you guys said, so okay. You guys, I don't want to bring them in either, you're fine. That would be a lot.
well, if
So everybody, no, listen, that's not a good road to go, because holy shit, you just have to sort of stumble on the answer that way. So let's be a little more specific. Remember what I said, any freaking time I ask you for the domain of any function in the universe, can you say in English what must be true? The inside of a square root must be greater than or equals. Must be non-negative. You guys with me? Say in English what must be true about the function that is there. Inside must be non-negative or at least 0 or however you want to say that, yes? Now pretend like that's English. That is some weird variant of English. Inside Now write what I just said in Mathish. Must be non-negative or must be at least 0. Yes? Can you guys see a smart way to solve this? Because we're talking about a region, yes? And a region could be a square. It could be a parabolic, like we just saw, yes? The outside of a parabolic function in the xy plane. That could be the region we're talking about, correct? In this case, it's the other thing I said earlier. Bless you. You guys have to start looking. I'm not trying to solve for x. I'm not trying to solve for y. Bless you. I'm trying to put this in a form so I can see what shape I'm making in the xy plane. So how do I do that?
Solve for 16,
Yeah!
and then divide by the negative.
So I get x squared plus y squared is less than or equal to 16. Is that cool?
Yes.
I added these over and then I turned the whole thing around. Is that okay? So can somebody just tell me very quickly? What about 4?
Then we go greater than 4.
So all the points I'm allowed to use for G must come from where? No. Come on. Stop.
Circle a region that is.
Thank you.
Which is a circle which is at the origin, radius of 4 on
Yeah.
the xy plane.
Yeah, so every point I'm allowed to use must come from the interior of a circle centered at 0, 0, radius 4. Can I include the points on the circle itself?
Wait, yes.
Doesn't it say I'm allowed to equal?
Yes.
Do you guys see that? Do you guys see how the math of it matches with the geometry of it? Why couldn't I use the points on the parabola we had earlier? Because the thing I was working with said less than. It didn't say or equal to, yeah? So of course I couldn't use the things that actually made it equal because the thing didn't say I could use the things that make it equal. This one, I'm not allowed to use the points that make it 16. And what points are those? The ones on the circle. Is that cool? So you could graph the domain of this function. So you could see, I could give you this problem on, I don't know, a quiz or something. And I could say, plot the domain. Yes? What's involved in that? Algebraically simplifying to a point where you can identify what the picture would be, and then you make it. Does that all make sense? So in general, the domain of a function of 2 variables will be some region in the xy plane, potentially the entire xy plane. And that would be funny if I made you graph that, it was just like shading in the entire xy plane. Right? No, I'm not going to. So if I wanted to graph this, it would just be, ha-ha, hee-hee, woo-hoo. By the way, what exactly am I graphing? Is this the function? The original function? Where is this function related to what I just drew?
Be above it?
It would be up here, yes. Cool, I love it. Yes? What if I have 0, 0 as an input? What would the output be? 4. So the input for input 0, 0, output of 4. And then everything else from that goes down. So you can it's the dome. It's the dome from earlier, yes? Stephen King, it's one of his better later books, The Dome. Yeah, it was pretty good, the book. The TV show sucked. I only watched like 2 shows. Again, sorry, that's not a prerequisite for the course. Okay. Do you guys see the idea of it? You might be uncomfortable with some of the math, but you see what you need to be able to see before you can do a problem is, what the hell is the point of this? What am I trying to get? So if I ask you for a domain of a function of 2 variables, you are trying to get to the point where you could graph it if you needed to. Yes? It is a piece of the xy plane. So to finish this graph, what should I do? Yeah, because now if I try to use this point, what would happen? Let's say that point is like 5, 4. Yes? If I try to use 5, 4, like I just said, that'd be 16 minus 25 minus 16. That's major problems, right? That's plus or minus 5i, and we don't want to deal with complex numbers. You guys kind of with me? A little bit? Okay. All right, let's mess with the same function. Yeah. Okay. We'll do one more thing after this. That's a G. Believe it or not. How would I find a level curves? Somebody remind me what it means, what a level curve means. The slices. And where do you slice? You slice at a certain height. So a certain value of z. So you want to make z a constant. If I make z a constant, I get the slice at that height. Does that make sense? So piecing together what we did earlier physically with what we have to do mathematically. So if I'm going to get a slice at a certain height, just like I did, you saw in Desmos. I don't know if you guys paid attention. I had z equals k. So I was setting z to be a certain value, and then I could slide k. And that's why I was able to go up and down with it. Yes? Maybe? So I was slicing it at a certain sense. So just replace g of xy with k. Now solve this a little bit. Square both sides, yeah? Add over this business, subtract the k squared. What do you get that? What do I get? Not surprisingly, for my dome, I should have said this first. Man, I was smart. I really so much use. So if I had a dome, yes, and I said at a certain height, what shape would you curve out if you took a cross section? You of course would get a what in my dome? Freaking circle. That's what we just found, yes? For a given k, if k is 0, where am I if k is 0? Where am I physically if k is 0? XY plane. Is everybody with me? If k is 0, I'm at a height of 0 of the xy plane. I'm in the xy plane. What is the level curve at k equals 0? A circle of radius 4. Is everybody with me? So let's do this. Let's all make a graph with horrible scale. If I do this, oh my God, this is more like Stewie's head. We'll be all right. Stewie's head when he had the mumps, I think is what's going on here. This is a level curve, and I'm going to put next to it k equals 0. Yes? 4, 3, 2, 1. Okay. What if k equals... There's no good numbers here. What if k equals... you can do it, Jeff. K equals the square root of 7. What do I get?
9.
You guess, all right, see, that's why I picked square root of 7, yeah? So if I ask you, draw several level curves in the xy plane. So what we're effectively doing, does everybody see what this function looks like? Remember, it's a dome, yes? It's a dome, you with me? What if I flatten it? Yes? It's almost like a pop-up book thing, yes? You guys ever seen those spherical lantern lights you can put in trees? If you ever got one, they come flat, and then you unflatten them. So when they're flat, you can see the level curves on them. When you stretch it out, and you can see that curve that's actually on the surface of the sphere itself. That's a beautiful level curve, right? If I was a better teacher, I would have brought one with me because I have some at home, but I didn't do that. I suck. I think maybe my head was on other things. So what we're about to do is we're about to just smush it, and we're going to graph the level curves that represent. So we're going to make a topological graph of our function. So if k is square root of 7, I get that. What is that? This is a circle of radius 3. So I'm going to do a circle of radius 3. Centered at the origin, of course, is a background. Kind of like in the background. Pretend it's a circle. And next to it, I'm going to put k equals square root of 7. Yes? Just to cut to the chase, if k equals 4, this is where things get weird. Not really weird, but what if k equals 4? No, if k equals 4, 16 minus k squared, right there, right? You get 0. And what's x squared plus y squared equals 0? It is something. It's only one point that works. So I put a point at the origin, and I say k equals 4. You see that? Now I could have a couple more around that, but you see how it would be the same. I could pick smart things. I could pick square root of 12. Why would I pick square root of 12? Because then the radius would be 2, yes?
So if I ask you, graph several level curves for this function, you do the extremes for sure, like 0 and 4, and then you just pick smart numbers between if you want to. You can pick dumb numbers if you want to, but I'm going to pick smart numbers because I'm the one making the graph, Jeff. Does that make sense? All right, so several things there. You will have to graph the domain. That is separate from this. Is that cool? This one just happened to have, it kind of looks like it's domain, but why does that make sense? Because this actually intersects with the x-axis and stops. So it sits on its level curve. Does that make sense? Does every function do that? No. Because I could have a function that goes through it and continues, and so its domain would be bigger or whatever. Okay, maybe. I love you guys. Some of you guys look so despondent. I'm sorry. I love this shit, and you guys, good for you. Okay. All right, so last thing for today. I promised you I was going to do one more thing after that. Just to give a little preview of what we're about to get into. What was your favorite? Oh man, there's no one nice way to do this. What was your favorite part of calculus? And I'm being sarcastic. What was your least favorite part of calculus?
Oh no.
Man, Jeffrey, you walked right into that. I'm sorry. I'm really sorry. We're going to have very prescribed ways of analyzing some of these limits. I need you to understand. These are going to be difficult. The work you guys have to do, I'm going to try to make it so you have some more prescribed kind of things you have to do. You with me? Because these, I need you to really get why they are difficult though. In 2D, how can I approach a point? From the left and from the right, yes? Of course. Right? What if you're my point in my XY plane? Yes, I'm sorry. I'm taking on you. You okay with that? No, it doesn't matter because I've already done it. No, just do it. Just get it over with. How many ways can I approach him?
Forward.
I just go straight. Hey, what's going on, man? Right? Or do you go? Yeah, I need you to understand. If there's a point, so how do I do a limit? I do the limit as the input approaches something. What does the output do? Correct? What are my inputs for these functions? Points. So the limit as xy approaches some point. What are my outputs doing? How can I approach a point? Straight line. A parabola. I'm coming. Right? I can approach exponential. I can approach square root. Yeah. In order for the limit to exist at a point, every approach to it must have the same output. Because in 2D, what does it mean for a limit to exist at a point? Number one, the most important thing is the limits from both sides better freaking. They better, the limits from both sides better. Agree. Yes? They must approach the same point, yes. So if I don't approach the same point, the limit does not. Why is that so easy? Because I got this way and that way. If I have 2D inputs, again, does everybody get the problem?
Yeah.
I could go straight at him down the axis, right? Just jump over Zach. Zach's like, dear God, make it, old man. Right? Just right in the face. Oh, I'm not going to do it, I'm sorry. Then I'll understand why you're not in my next class. You're like, remember, you kind of booted me in the face. All right, sorry. Right? I could go straight down the axis. I could make a triangle. I can go this way, and then I could go that way. So understandably, none of us, well, yeah, there are problems that none of us could do in this, that we could look at in this section. So we're going to look at very specific types. And we're going to talk about very specific things we could do in those situations. But I need you to understand, the level of complexity increases so much the minute I let the inputs be points that exist in the plane. The number of paths I can take somewhere just went crazy. They didn't double. They didn't triple. They freaking infinitable, right? I'm not making you feel good, I'm sorry. But hang on this. Hang on what I said. What are you going to be expected to do? Specific types with very kind of recipe-ish ways. We will talk about some of the more esoteric, kind of weird shit. Yes?
And just to give one example of what I'm talking about. I'm like, damn it, I thought he was gonna shut up. Let me ask you this. So let me give you an example. Let me at least show you what this thing looks like. So far, so good. Look at that. The limit as the points we're inputting approach the origin of, for example, this function. Now, real quick, do you guys remember, as much as you hated them, what would you look at before you even started to do a limit problem? Is it indeterminate? If it's not indeterminate, that means I can determine the answer, right? That's why I love that name. It's a perfect name. If it's not indeterminate, I can determine the answer. I'm basically done. Yes? Is that indeterminate? Why? 0 over 0. So, do I know the answer right now? Ain't none of us know the answer right now. Yes? Actually, I do. Because I made a problem. Good for you, Joe. How the shit can I investigate this? I'm just going to lay down what we're going to do. We'll do it next time. But what was the very first thing you guys did? Oh, good Lord, no. Sorry. No, I say that way because a lot of my students did it because tutors showed them. I'm like, you don't know that shit yet. When you first learned limits, and I know this is 2 semesters ago. When you first learned limits, you looked at a table of values, correct? If I wanted to approach 4, I would do 3.5, 3.9, 3.9. Remember that? Remember that? You don't remember it? So you guys are like, I have pushed that so far back. That entire chapter 2, I ripped that shit out, Jeff. Just like on freaking Dead Poet Society. Rip that shit out. Nobody knows Dead Poet Society? Thank you. Remember that when they ripped the shit out? Okay. That's fine. It's not a prerequisite, I guess. It is a prerequisite to life. Watch the damn movie. So next time, we'll talk about 2 things. We're going to talk about how to create something that would sort of be like the table you guys made. It's going to be more complicated, yes? Because what we just said is an infinite number of ways to go. We're going to create a table to show if this at least looks like it might exist. And then we're going to talk about, okay, let go of the table. We're not going to do a table every damn time. It's going to drive us insane. We're going to talk about more algebraic kind of ways we can investigate this. Dear God, let there be some. Yes? Okay, that's enough. That's enough. Okay. If you didn't get your test back, let me know. Otherwise, I'll see you guys on Wednesday.